So first we are going to look at how do we implement a dictionary uh, in more detail. So recall that there are two terms, vocabulary and dictionary. The vocabulary is just the set of terms that are stored in the dictionary, and the dictionary refers to the actual implementation of the vocabulary. So we are going to focus only on the dictionary part of the index over here, and we're going to see how we can implement a dictionary. And as before, I would like to again repeat that we want the dictionary to be stored in main memory. So the dictionary data structure is going to store the term vocabulary. It's also going to store the document frequency as we've seen before, and it's going to store the pointers to the postings list. Now the question is, how do we actually implement a dictionary? This is just a picture of the standard inverted index. So I'm going to call this a standard inverted index because we're going to see some other kinds of indexes in this chapter. So when I refer to the phrase standard inverted index, this is the inverted index that you've seen from chapter 1. Here's the simplest way to implement a dictionary. Okay, diagrammatically you can just think of storing all the terms in a sorted array, an array of structures where the terms are sorted lexicographically, and you're storing the document frequencies as integers alongside the terms, and you're also storing pointers to the postings lists alongside the terms. So this is a structure. This is a struct. It stores a string corresponding uh, to the term. It stores an integer corresponding to the document frequency, and it stores a pointer corresponding to the postings list. And this is an array of structures. This is the simplest way you can implement a dictionary. Now, if you're searching for a particular term in the dictionary, you can use something like binary search here. If you're implementing it in an array of structures, and that's going to take you about log n time, where n is the size of this array. So let's assume that each term is approximately 20 bytes or a maximum of 20 bytes. We could use a 4-byte integer to store the document frequency, but as you know, what's the maximum size of an integer that can fit into a 4-byte word? It's about 2 to the power 32, approximately 4 billion or so. But in a web corpus, you're going to have a lot more than 4 billion documents, right? So the value of the document frequency can be much larger than 4 billion. So you may have to go for an 8-byte integer to represent this. So later in chapter 5, we are just going to start with this kind of a naive implementation, and then we are going to see how we can compress the dictionary and also compress the postings lists. So right now the size of the dictionary would be given by 20 plus 8 plus say 8 bytes, which would be 36 bytes for each of these rows, and 36 times the number of terms in the index. That would give you the number of bytes taken up by this implementation. Now, how are we going to look up elements at query time? We'll do binary search, narrow down to the term of interest, and then we'll follow the pointer to the postings list for that term. Let's look at more sophisticated ways of implementing a dictionary. This was a very naive implementation. There are broadly two main choices for implementing a dictionary. The first is a hash table, and the second is a search tree. Some systems use hash tables and other systems use search trees. Let's look at hash tables first. So I'm just going to give a very high level overview, and I would recommend that you go and look up these data structures in a data structures or algorithms book. So in a hash table, what you have is you have a hash function which takes in a key and maps that key to an integer. This integer, okay, what is the key here? Basically, you want to store a list of items. Okay, so let me explain this using an example. Let's say you want to store a set of numbers. Okay, and your numbers are 1, 2, 3, 4, 5, and so on till the number n. How do you store this list of numbers? Well, you can just store this list in an array. Now imagine that these numbers are not just uh, integers, but let's say they also have some metadata, meta information associated with it. So these are IDs. These are IDs for maybe employee records or your entry number or your social security number or whatever you're trying to store. And along with the numbers, you're trying to store some other information like name, salary, and so on. So think of each of this as a structure instead of a single integer. Okay. The integer field of this structure is the key because this is the value that's going to be unique for each person. So each of you can have your own social security numbers, for example, or entry numbers or roll numbers or whatever you call them in your university. So if you want to store information about n students, what is the simplest way to store them? Well, you can take an array of size n, store the record for student with entry number 1 in the first place position of the array, store the record for the student with entry number 2 in the second place, and so on. So if I want to find out information about student number I, is the student with roll number I just need to look up the ith position in this array. Now suppose these numbers had been instead of 1 to n, suppose they had been 2, 4, 6, 8, 10, and 2n. Now these may not be roll numbers, but let's imagine that roll numbers have necessarily to be even numbers for some strange reason. So these are n roll numbers. All n of them are even integers, but all of them are in the range from 2 to 2n. How do you store a record for? How do you store all the records for the students now? Well, you could store the record with roll number 2 in position 1. You could store the record with roll number 4 in position number 2. You could store the record for roll number 6 in position number 3, and so on. And in general, you would store the record. So the index of the record 2i, sorry, let me write it here. If I want to find out where the record for a particular roll number is stored, I can just take half of that and I will get the index in this array where I need to look up to get information about that record. Now in general, so these were very, very simple examples where you had numbers from 1 to n and 2 to n. But let's say you had a general list of n integers. How would you store it? How would you store it in such a way that can look up the record in constant amount of time? Note that calculate the index at which a particular record is stored, you just take a constant amount of time to calculate what the value of the index is. Just take half of that roll number and you'll get that value. But if you had a general list of n integers, you would need some sophisticated mathematical techniques to ensure that you would need a function f which would take your roll number and map it to some value or to some index in the array. And what you want is that for different roll numbers, your values need to be different. And you want that you should be able to calculate this function in a constant amount of time, just like here. And you don't want two different roll numbers to map to the same value. Note that one way to store this list is as a search tree, right? You can build a binary search tree or something like that. Are you familiar? You're familiar with binary search trees, right? Or is that also something some of you don't have a background with?
So we're getting some noise, so
Is one of the microphones on there? No, I can still hear my echo. Okay. Are you familiar with binary search trees? Are you familiar with the fact that if you're given a list of integers, you can store them in a binary search tree. You can search, given an integer, you can search for it in the binary search tree by, oh,
yes, sir.
you're familiar with that. Okay. But the problem with binary search trees is that in the worst case, you would need about order log n time to answer, to retrieve a record. Right? If you're given a roll number and you're storing all the records in a binary search tree, you may need order of log n time to be able to hone down to that record. Okay, I'm assuming you know what this means. In case of a hash table, you don't need order log n time. You need just a constant amount of time. Because all you need to do is you need a good hash function f which will take your roll number and apply a mathematical formula to end up with a value which you can just look up, which you can treat as the index in an array and look up that array at that index and you'll see your record over there. So if you had 100 roll numbers to store, you can apply this hash function on all those 100 roll numbers and you'll get a value. You'll need to predefine the size of your array. So if you define the size of your array as having 100 elements, then this function will need to return a value from 1 to 100. So given a roll number, you will hash it to a value between 1 and 100 and then store that value, store the record at that index given by this value. Now a good hash function is going to distribute your records uniformly over this entire range. So it won't map different roll numbers to the same value. But at the same time, it's going to ensure that if you calculate this formula, if you calculate the value of this function for this roll number, you should be able to get the value in a constant amount of time. So instead of hashing roll numbers, we can also hash terms. We can hash terms in the vocabulary to some index in an array, and we can store that particular term. We can store this particular structure that we saw in the previous slide. So I can take this hash function, calculate the value of the hash function for this term. So this f applied on this string AACHEN will give me a value, and I'm going to look up the array at this index, and I'm going to store the record, the entire record for this term. I'm going to stuff it into the array at that index. So if I get a query and I have to look up the postings list for that particular term, I'm going to apply the hash function. I'll immediately know at what index I need to look up in the array. I'm going to look it up. I'm going to get the record for that particular term. And from the record, I can retrieve the postings list for that term. So this is in brief how you would use a hash table to implement your dictionary. Any questions about this?
So, no, sir.
Okay. Now, there are certain downsides to using a hash table to implement your dictionary. Firstly, if you have a term like judgment, which is written in different ways in Britain and America, so this is this is the spelling of the word in American English, and this is the spelling of the word in uh, British English. Suppose I want to search for the term judgment in the dictionary. Now I know that there are two variants of that word. A hash table is not going to allow me to get both of them at the same time, right? Because the value of the function for the string judgment could be very different from the value of the function for the string judgment with the e. Okay, the hash function could map one of the variants in the first few elements of the array, it could map the other variant somewhere in the middle of the array. So the records for particular terms, variants of terms, can be pretty spread out all over the array. And there's no easy way to retrieve the records for all the variants. A hash table does not allow you a prefix search. For example, I can't, there is no easy way for me to retrieve the records for all terms starting with the word JUDJ, starting with the letters JUDJ, because there could be hundreds of words with matching this pattern, and the records for all 100 of them could be spread out all over the, all over the place, because a hash function usually tries to randomize the value to which it maps the key. So you can't do prefix search on in a hash table. You can't find minor variants of terms in a hash table. And moreover, if your vocabulary keeps growing, let's say in the context of a web, you get newer and newer terms appearing over time. What's going to happen eventually is that your hash function is going to it's going to start mapping different terms to the same value. Because if it's trying to randomize things by spreading them apart, occasionally you're going to get something called collisions. A collision is an event when two different keys get mapped to the same hash. And usually, there are standard techniques of dealing with collisions. One is to store all the records at that place itself, but create a linked list from that slot instead of, storing just one record at that place. You store a linked list of records there. And I mean, there are different ways to deal with collisions. But basically, you're going to get more and more collisions as your vocabulary keeps growing. Because, the range of your hash function is going to remain the same, right? 1 to 100. But if there are going to be 200 words, then you're going to have instances where many terms are getting moved to the same slot in the array. So in that case, what you may need to do is re-implement your hash table. That is, come up with an entirely new function f, having a different range, a range from 1 to 2, and randomizing the keys across this whole range so that all the items are more or less placed in different slots with, maybe occasional collisions, but not too many collisions. So a dictionary can be implemented just as a sorted array of structures or as a hash table. A third way, which is probably the most powerful way to implement a dictionary, is as a search tree. Now you're probably familiar with binary search trees. In a binary search tree, you have uh, basically internal nodes and leaves, and each internal node has at most two children. It can have zero children, one children, but at most two children. And the binary search tree satisfies the property that all the elements in the left subtree of any node are less than or equal to the elements in the root. And all the elements in the right subtree of the root are more than the element in the root. By less than and more than, I'm assuming there is some kind of ordering between the keys. Now, if these are strings, you can think of the ordering as corresponding to alphabetic ordering, or what they call as lexicographic ordering. So lexicographic ordering is an ordering assumed between characters, so that given any two strings, there is a well-defined way to say that this string is less than this string. Okay. And the strings need not contain only letters, they can also contain numbers. So it's alphanumeric ordering. Now a binary search tree satisfies this property at any node. This means if I take this particular node, then all the elements in the left subtree of this node will be less than that node, and all the elements in the right subtree of that node will have key values larger than the key stored in this node. So again, what you're trying to store here are a set of keys in the form of a tree, and given a key, you want to look up the record for that key in this data structure. And a binary search tree allows you to do that in order log n time, where n is the total number of nodes in the entire tree. Now, the problem with just using a binary search tree is that if you just insert the elements in sorted order, then the algorithms that do the insertion and deletion, again, we don't have time to go into those algorithms, but the insertion algorithm into a binary search tree will actually end up creating a linked list out of it. If you insert the elements in, say, increasing sorted order, you'll get a structure like this. Okay, 1, 2, 3, 4, let's say these are the key values. Now this is also a binary search tree, but the problem is that this is not a balanced binary search tree. A balanced binary search tree is one which will distribute the nodes evenly. Okay, so it's going to look something like this intuitively. It's not going to look it's not going to look like this. Okay, it's going to look like this. So if these 6 elements had not been stored in the form of this linear chain, but had been stored in the form of a balanced binary tree, then the height of this tree would have been much less. Okay, I'm just giving a very very intuitive description here. The advantage of using a balanced binary search tree is that because of this triangular shape, because of the nodes being equally distributed across all the levels, I mean, starting from the first level, you fill in both the children, then you fill in both the children over here, and so on. You can show mathematically that if the total number of nodes in this tree are n, then the height of the tree will be log n, at most log n. So if you want to search for a particular record, you'll start from the root. You'll check if your record is less than the root or more than the root. If it's less than the root, you will move to the left child of the root and start searching in the subtree rooted at this left child. Again, you'll compare the value of the key that you're searching with the value that is stored in this node. If now your key turns out to be larger than the than what you're storing in this node, then you'll move to the right subtree of this node. So in this way, you'll keep going down and down and down until you hit the value that you're looking for. And that can take at most log n steps because the height of this tree is at most log n. So this diagram shows the terms stored at the bottom level in alpha, in lexicographic order from left to right. Notice that this is true for every node over here. So everything to the left of the root, all the strings that are stored in the left subtree of the root are strings that start with the letter A or B or C up to M. So these are strings starting from A to M. All strings starting from N to Z are stored in the right subtree. Then if you look at this particular node, everything to the left of this node, everything in the left subtree rooted at this node corresponds to strings starting with A and going up to strings starting with HU. And everything in the right subtree over here corresponds to strings starting with HY and going up to strings starting with M. And finally at the leaf level you have these actual terms. Okay, so these are records for the actual terms. And if you're able to search and retrieve a particular record, you can look up the pointer to the postings list for that term, follow that pointer and retrieve that postings list from the disk. So this is approximately how search trees work. When search trees are used to implement the dictionary, this is how they work. And there is a particular kind of tree called a B tree, which works pretty well for this purpose. So the B tree is a balanced binary search tree, and different balanced binary search trees have different kinds of properties, and based on what kind of properties they have, those trees have different names. You have something called AVL trees, you have something called red black trees, you have B trees, and there are other kinds of trees as well, splay trees and so on, all of which are balanced binary search trees. Now if you look at a B tree in particular, a B tree is defined to be a tree whose such that for every node in the tree, the total number of for every internal node in the tree, so all the nodes at this bottommost level are called leaf nodes, and all nodes above this bottommost level are called internal nodes. So internal nodes are nodes that have children. Leaf nodes are nodes which don't have children. So this node would also be a leaf node by that definition. But in a B tree, all the leaves are at the last level or at the penultimate level. Okay, because the last level, if the last level gets filled, then you'll need to percolate down to an extra level. But actually the strict definition of a B tree is that it's a tree where every internal node has a number of children in this particular interval a comma b. So if you're looking at a 2-4 B tree, it's a tree in which every node has at least 2 children and at most 4 children. So the number of children of every node here vary from 2 to 4. It could be 2, it could be 3, it could be 4. But you'll never have a case where a particular node has exactly 1 child. Or you'll never have a case where a particular node has 5 children. So B trees are the usual way to store, the usual way to implement a dictionary. And one of the reasons for creating this range from A to B, I mean, think about it intuitively this way. If you allow every node to have, say, 100 children, then what you're going to have is, compared to a tree where every node had only 2 children, a tree with 100 children is going to look like this. Okay. So as you go down from the root to lower and lower levels, the number of nodes at that level are going to increase drastically, and the height of the tree will be smaller compared to this particular tree. So by allowing every node to have more and more children, you're going to flatten out the tree so that the height decreases. But on the other hand, you will need to make more number of comparisons to decide from each node which of the paths you want to take. Now you don't just have two paths, you have more than two paths. For example, here you have three paths. And what path you take in your search will depend on whether the key that you're searching for falls into this range or this range or this range. And you'll have such ranges for every level. Now, the good thing about a B tree is that it allows you to do a prefix search, because all, all nodes that start with A are going to be stored somewhere in this subtree. And even within this subtree, they're going to be bunched up together. So if I'm searching for all terms that start with the characters J, U, D, J, I can just follow J, U, D, J down this particular B tree. And once I reach a particular node, let's say after reading this whole string J, U, D, J, I've reached at this level. Now everything below me I know is going to be some suffix, but the string that what I've seen so far, the prefix that I've seen so far is JUDJ. So I can just collect all the nodes that are under me, and all those nodes are going to store records where the terms start with JUDJ. So I just collect all those terms, I look up their postings lists, and I take their OR. Note that this query JUDJ followed by an asterisk is a query asking for all documents containing terms that start with JUDJ. So judgment with an E is one of those terms. Judgment without an E is another of those terms. Just the word judge would be yet another term. So using a B tree, I can collect all those terms pretty efficiently because they're all going to be stored next to one another in the tree. So I can just traverse the tree in an efficient way, collecting all those terms, and that will allow me to get the postings list for all the terms satisfying this particular pattern. So I just take all the postings list, I do an OR operation, because this that's what this wildcard query is. Any word that starts with JUDJ is a good candidate word to whose presence you want to see in the corpus. So you'll take all the postings lists, do an OR operation on them, and then return the results you get. And that's how you would answer a wildcard query like this, where you have a string at the beginning and a trailing wildcard at the end using a B tree. So a B tree solves the prefix problem that we saw in a hash table. You can search for terms starting with a particular string pretty efficiently. But the problem with respect to a hash table is, of course, that instead of taking a constant amount of time, now you're going to take time proportional to the height of the tree, which is going to be log m, where m is the total number of elements in the tree. And this assumes that the tree is balanced. Otherwise, you'll get that linear chain that I mentioned for binary search trees. And of course, B trees are always balanced. So If you just have a B tree, you don't need to say that it's balanced because that's part of the definition. It follows just from the definition of a B tree. If you constrain each node to have at least two children and at most four children, or in general at least A children and at most B children, you can show that the height of the tree is going to be logarithmic in the number of nodes. And B trees don't need to be rebalanced because the very way in which insertion and deletion operations are defined on a B tree ensure that the tree is balanced at every stage. Whereas in a binary search tree, a sequence of insertion and deletion operations may actually end up skewing the tree, and you may have to do some kind of global rebalancing periodically. But with B trees, your tree is always going to remain balanced.